Hi everyone. In this Connect with Networking video, we will be discussing Chapter 8, Backbone Networks. Let's go ahead and get started. Backbone networks are the networks we use to connect other components of our larger scale networks. That might be connecting local area networks together or connecting our local area networks to our wide area networks and the internet. We break out backbone networks into two major categories: the distribution layer, which allows our local area networks inside a building to communicate with one another, and the core layer, which would connect our various buildings on a larger campus to one another. Most backbone networks use fiber optic for higher data rates and are based upon either switches or routers. Switches operate at layer 2, and as a consequence are often called transparent devices. They do not actually look at the IP address for a packet. Instead, they examine the Ethernet frame and then they pass the message along to the next device that has that Ethernet frame address. As a consequence, they don't actually remove any information and they don't actually create any information when they are moving packets from place to place on the network. Some more advanced switches are what are called managed switches, where you can configure them and manage them remotely using something like a spanning tree protocol. There are more advanced switches, which have sometimes been called VLAN switches or layer 3 switches, and they have features of both switches and routers built in. So they can operate at layer 2, where they're using Ethernet frames to move packets from one place to another, or they can operate at layer 3, where they're examining IP addresses and recreating new Ethernet frames as necessary. And the primary purpose of being able to operate at both layer 2 and layer 3 is to create virtual LANs, which we will talk about later in this chapter. In an earlier chapter, we discussed routers. Routers are still used for some backbone networks, particularly at the core layer. These are not transparent devices. When a message is received, the Ethernet frame is addressed to the router. The router removes that Ethernet frame, examines the IP address for the eventual destination of the data, and then creates a new Ethernet frame for the next destination for that packet of information. Routing, as a consequence, requires much more processing than a switch. As stated in an earlier slide, we tend to think about backbone networks in terms of different hierarchical layers. The access layer is how a user accesses their network, which is typically through a wireless local area network or a local area network. The distribution layer is how we connect various local area networks within a building to one another, where the core layer allows us to connect various buildings on a larger campus to one another, or reach out to our wide area network or internet. We're going to break down the three major types of backbone networks, but in practice it is common for us to see a combination of these architectures across a larger campus. Switched backbone networks are typically used at the distribution layer, and because most businesses have a distribution layer where multiple local area networks inside a building communicate with one another, switched backbones are by far the most prevalent type of backbone network. Backbone networks that use layer 2 switches operate transparently, where they do not modify any of the data that's being sent from one location to another. They receive Ethernet frames and then move those Ethernet frames to the appropriate next destination without examining or changing anything else in the data. Switches come in a variety of different form factors. Some of them could operate at the desktop level, where they look very much like a desktop computer. But most switches are going to be rack-mounted or chassis-based, where they're installed inside a main distribution facility, like a wiring closet or a server room. Switched backbone networks are a star topology. Every individual device that's connected to a switch has its own dedicated pathway, and every device would pursue collision tolerance using the collision detection protocol, but because of the star topology, the chance of a collision on a network that is based upon switches is very low. From a logical standpoint, the way you can think about a switched backbone would be individual local area networks connecting to their own individual switches, and then all of the switches connecting to a parent switch, which replaces the traditional cabled backbone network we would see in routed networks. So in this case, if a piece of information wanted to flow from the upper left local area network to the bottom right local area network, a computer in the top left would address a message with the Ethernet address for a computer in the lower right. That frame would be received by its switch. The switch in the upper left would send that Ethernet frame to the parent switch. The parent switch sitting in the middle would send that Ethernet frame to the switch in the lower right, and the lower right switch would send that packet to the appropriate computer on its local area network. All of that would happen at layer 1 and layer 2. None of the other layers would ever be affected or even examined. While this diagram shows how things are operating from a logical standpoint, physically things are probably arranged much differently. This is a picture of a switched backbone network where all of the switches are located in the same location. So while in the previous slide it looked like switches were close to the computers in their specific local area networks, that is probably not the actual case from a physical standpoint. Switches are probably located remotely from the individual clients, but close to one another. In this particular picture, there are multiple patch panels and multiple switches that are communicating with one another. And on the next slide, we have a diagram of what is happening in this picture. At the top of the bottom of the previous picture, we have a layer 2 chassis switch, which has multiple 100 megabit per second ports for each of the individual switches that manage each of the individual local area networks. That top layer 2 chassis switch is effectively the building's distribution layer backbone. Each of the individual switches, which are located underneath that chassis switch, are the access layer for the local area network, allowing each of the individual clients to communicate with one another or with the backbone network. And each one of these in this case is a 100 megabit per second switch. You'll notice there's one additional component to the layer 2 chassis switch, which is the gigabit per second fiber optic port on the far right. And that communicates with the overall building's backbone that might reach out to other buildings on campus. Here's another diagram of how things might operate from a logical standpoint. Again, physically, all of these switches are probably located close to one another, perhaps in the basement together. But from a logical standpoint, each individual switch operates close to its individual local area network or operates to control the entire floor of a building. So in this case, you can see there are multiple layers of switches, switches for each local area network, switches for each floor, and then switches for the entire building. And then you can see a transition from a switch to a router when we move outside of the building. The campus backbone in this picture looks like it's going to be a routed backbone network, which is pretty common for core backbones. Routed backbones are sometimes called subnetted backbones or hierarchical backbones, and they are much more common at the core layer, though we still see some routed backbones at the distribution layer. One of the major advantages of routed backbones is LAN segmentation, where individual local area networks can be separated and routers act as traffic cops, not allowing certain packets of information to ever leave a local area network. Because the router looks at layer 3 and examines IP addresses, it can potentially stop traffic which is not meant for other parts of the network from ever leaving one specific location. Switches can't do this. So routers do provide an additional layer of safety and security that we don't get from switches. The downside is because the routers have to use layer 3 to move packets from place to place, they are a destructive/constructive process, which means they tend to be slower, they tend to be more expensive, and they tend to be harder to manage. Here is a logical picture of a combination of backbone switches for individual buildings connecting to routers that allow all the buildings to communicate with one another. You can think of the routers that are part of each building's network as the traffic cops that only allow traffic out onto the core backbone when it really is meant to be there. If traffic is not meant to be directed to the core backbone, the router will prevent it from entering that backbone area of the network. The core router itself is just connecting all of the various buildings together. or directing traffic to the internet router, which allows you to reach outside of the business's internal network. A third alternative to switched backbones or routed backbones are virtual local area networks. The idea here is that we can arrange various clients not based upon their physical location, but based upon some other logic. So think about having computers that are all in the same office suite that belong to multiple different local area networks based upon a person's job responsibilities. Normally, computers that are close together all connect to the same piece of network hardware, a switch or a router. But if we wanted our devices to not be configured based upon the equipment they connect to, because they have different responsibilities and need different resources, we can use a virtual local area network to create LAN segmentation that would allow these devices to share the right resources with other computers anywhere else in the building or anywhere else on our network. This is a much more complicated system and is much more challenging to manage, and it is typically only used in large networks, and even then only when necessary. Pictorially, from a logical standpoint, a virtual LAN is much different than what we've seen before. In this picture, you can see that every single computer in the building is using one switch. From a logical standpoint, the three computers in the top left might actually think of themselves as part of their own local area network, which is segregated from the rest of computers in the building. They might share printers, they might share a file server, and they might not share those resources with any of the other computers that are physically connected to the same hardware device. But the switch at the center of this network is much smarter than a typical switch and can do segmentation of the network from a virtual software standpoint as opposed to a physical hardware standpoint. So different devices on this network can operate as if they were part of a local area network separate from the actual larger local area network they are physically part of. The way a virtual local area network operates is by giving every device a virtual LAN ID, which is mapped to a traditional IP subnet. So much like routers using subnets to identify whether you're part of a local area network or you are addressing message to something outside of your local area network, virtual LANs use that same structure to address messages to inside your virtual local area network or outside of your virtual local area network. Virtual LANs are transparent, but they do require a router or a layer 3 switch to coordinate messages from place to place. The simplest version of a virtual LAN is a single switch that allows for more than one virtual local area network to operate on the same piece of hardware. So in this case, a single layer 3 switch actually has two virtual LANs. The devices on virtual LAN 10 would operate on one subnet, and the devices on virtual LAN 20 would operate on a different subnet with a different set of IP addresses. Even though physically all these computers are part of the same physical local area network, there are two virtual local area networks, so the computers think of themselves as part of two separate networks. It is also possible to pursue a multi-switch virtual local area network. This is much more complicated and actually requires some different protocols that allow for an additional tag to be inserted into an Ethernet frame to encapsulate the frame and decide how to actually address and transport that data. In this picture, you can see three virtual local area network layer 3 switches, three different virtual LAN IDs, 10, 20, and 30, with three different IP address subnets. If you're part of 179.58.7, you're part of virtual LAN 20. If you're in 179.58.10, you're in virtual LAN 10. And if you're in 179.58.11, you're in virtual LAN 30. So even though individual devices might be all connected to switch 1 or switch 2 or switch 3, different devices on the same switch might belong to different virtual LANs based upon their IP address and will have access to different resources and move their data from place to place using a different protocol than what we've seen before. This is obviously very complicated, but in certain scenarios on very large networks, configuring your network using a virtual LAN is a more efficient way of managing your resources. The biggest advantage of a virtual local area network is much more flexible subnetting. We can manage traffic flow, which might lead to better performance, and we can prioritize certain traffic. Some local area networks on a virtual LAN will get priority over other devices. The downside is this is really complex, and it might increase management when memberships change. If a client has to shift from one virtual local area network to another, that can be challenging. Layer 3 switches are also more costly than Layer 2 because of their additional capabilities, and so there is an additional cost to using a virtual LAN. In terms of the best practice for a backbone network, a switched backbone has the best cost to performance ratio, especially at the distribution layer, so that is why we see switched backbones on almost all distribution layers at this point. And we're starting to see more switched backbones even at the core layer. However, for security and traffic management, routers are still a good choice for core layer backbones. And so many networks are still using routers at the core layer. Virtual LANs have become more and more widely used, especially for organizations that need the additional flexibility that they provide, but the technology is still relatively new, and so we have not fully explored how virtual LANs might expand in the future. In terms of the appropriate technologies, there's no reason for a modern company to pursue anything slower than a gigabit Ethernet for both the distribution layer and the core layer at a minimum. And when we get to the core layer, we are probably looking at more than gigabit Ethernet speeds as a requirement for larger businesses. It's also important for larger organizations to consider redundant devices and redundant connections so that they have robustness in case particular pieces of equipment fail or particular networks suffer outages. Pictorially, we would expect to see Layer 2 switches for the access layer and often Layer 2 switches for the distribution layer, although we might see Layer 3 if we're pursuing a virtual local area network. At the core layer, routers are probably the right choice, but if an organization is considering moving to a switched backbone network for the core, installing Layer 3 switches might be a smart option because this allows for virtual LANs and also allows you to pursue a switched backbone network should you choose to do so in the future. If your backbone network is not performing as well as you'd like, there are 3 places to focus your efforts: the individual devices on your backbone network, the circuits themselves, and the demand that's being placed on your backbone. In terms of implications for management, the cost and necessity of upgrading our backbone networks will continue to grow as our demand for network traffic increases. Virtual LAN backbones do provide additional flexibility, and they're becoming much more popular as a consequence, so I would expect to see more Layer 3 switches being used on networks or being installed for a just-in-case scenario. And as with local area networks, Ethernet is now the predominant protocol, which is why it's the only protocol we discussed in this chapter. That's it for now. Thanks so much for watching. See you next time.